Welcome back to the deep dive. We are continuing our crucial conversation around configuration management. That essential scaffolding that keeps modern software development from, well, collapsing into chaos.
Yeah.
We've already spent time on development and version management, talking about managing code conflicts and making sure everybody's working off the same foundation.
And that foundation, it leads directly to this next phase. For this deep dive, we are zeroing in on the automated build process. Our mission today is to understand exactly how we take that clean, checked-in code and turn it into something reliable.
A release-ready product.
Exactly. It's the translation layer between, human effort and what the customer actually gets.
Okay, let's unpack this. Based on the sources we pulled, the big question is actually pretty simple. Why go to all this trouble? Why automate the build? Why not just let a developer compile the code manually when a release is needed? That used to be the way.
It was the way, and it was fast, sure, for one developer on one machine, but that's exactly where all the risk was. The core problem of the old way is inconsistency and a total lack of any kind of audit trail. If the build relied on one developer's specific machine, maybe they had a custom setup, a different library version, something nobody else had.
The classic, it works on my machine problem.
Precisely. The binary you got might miscode that a colleague just finished, or, and this is much, much worse, it could accidentally include some unintended half-finished code that was just sitting on that developer's desktop.
But not properly checked into the system.
Not at all. The thing you delivered was tied to one person's setup, not the clean, official state of the entire project.
So this whole evolution is about swapping out that human flexibility for machine-driven consistency.
Absolutely, and that's the real nugget for you, the listener. Modern building solves those human error problems by strictly controlling the inputs. It's done on dedicated, separate computers, often virtual machines, with really rigid, uniform configurations. They draw input only from the version management system, the VMS, and from the requirement systems.
So they don't touch a developer's local files at all?
Never. It ensures total, auditable control over what goes into the final product.
That distinction drawing inputs only from VMS, that feels huge. So if we're relying on a machine, it needs flawless instructions, a blueprint. The sources call this essential info metadata. Can you walk us through that blueprint? What are the key points for any automated build system to even get started?
This is really where the discipline of configuration management comes in, because the whole process is defined by this metadata. We need 6 critical pieces of information recorded for the project before we can even think about building successfully.
6 points. That sounds like a lot of initial overhead, especially for a small team. Doesn't that slow things down at the start?
It's a great question, and it's a common pushback. But that upfront discipline is what saves you exponentially more time down the line. If you skip these, you are basically setting yourself up for chaos. Let's just go through the 6, and you'll see why they're non-negotiable.
Okay.
First, the simplest one. What is the project name? Just a clear, unambiguous ID. Second, what is the published release version? This is the external number the customer sees, like version 2.3. Third, and this is where the auditing power really kicks in, what is the build version?
And the build version, that's the internal tracker, right? Not for the public.
Exactly. And this number is designed to auto-advance with every single attempt to build.
Whether it succeeds or fails.
Doesn't matter, succeed or fail. If you try a dozen builds, you get a dozen unique build version numbers. It gives you a unique ID for every compilation attempt, which is just critical for tracking and for diagnostics.
So the release version might stay at 2.3, but the system is cycling through build 2.3.123, 124, 125. That is fantastic for debugging.
Yeah.
If a bug shows up, you know precisely which build attempt created it.
That is the power of it. The fourth piece of metadata is defining the high-level deliverables. Is this project making a mobile app, a set of database scripts, an API, a PDF? You have to define all the outputs up front.
And I'm guessing the 5th point is where you really get into the details of those deliverables.
It is the most granular and, frankly, the most complex. For each deliverable, you have to specify a ton of detail. What's its own version number? What kind of output is it? SQL and EXE, JavaScript documentation. And crucially, where are the source files in the VMS? Which branch, which tags? And then you have to note any build dependencies.
Dependencies. So that dictates the order of operation.
Precisely. If the mobile app needs the back-end API to be built first, the system has to know that. Without defining dependencies, the system is just, throwing code at the compiler randomly, which is a guaranteed failure for anything complex.
So it sounds like this ensures the system has all the instructions it needs before anything starts. What's the 6th and final piece?
The sixth point tracks the overall state of the product build, and it goes way beyond just built or failed. The sources really emphasize tracking the state from unbuilt through building, built, failed, all the way to pass to testing, and even failed testing. This metadata becomes the single source of truth.
So if we put it all together, these 6 points give you total auditability and control. If the metadata is incomplete, the system just stops. It prevents a bad build from ever getting into the pipeline. Makes that initial overhead totally worth it.
It's the foundation of quality. You just can't have a high-velocity org without this level of control.
Speaking of quality, let's talk about what happens before compilation. Because no matter how perfect your build system is, if the code coming in is broken.
Garbage in, garbage out. You get broken deliverables.
Right. And this is where the idea of gatekeeper processes comes in. What's the fundamental idea here?
The idea is prevention. The core rule is that developers have to unit test their code before checking it into VMS. But, people forget, they rush. The gatekeeper's job is to automate the rejection of that untested or broken code right at the entry point.
Instead of waiting for the big nightly build to fail and tell you 6 hours later, you're automating the rejection of the commit itself. That sounds brutal.
It is efficiently brutal. Let's look at that really great example from our sources about SQL scripts. They are notoriously fragile. A common and very powerful gatekeeper practice is to automatically parse these scripts during the check-in process, before the VMS is even updated.
Parsing, so just check in the grammar and syntax, not the logic, just the mechanical correctness.
Correct. The system doesn't care if the script is efficient, only if it follows the rules of the language. If that SQL script fails the simple parse check a misplaced semicolon, a typo, and a command, the check-in is immediately refused. The code never even gets in.
And the developer gets that feedback instantly. That is just incredibly efficient. Because if a script fails a simple parse check, it proves the code has syntax errors, which means the developer cannot have possibly tested it.
Exactly. And trapping that error right there at the entry point, it saves a massive amount of time later. It prevents that flawed script from ever contaminating the code base.
It's like an automated traffic cop for your code.
Okay, so once clean code gets into the VMS, the build starts. You mentioned there are 2 different paths: planned builds and continuous integration, or CI builds. Let's start with the big one, planned builds.
Planned builds are the heavy-duty production runs. They represent a deliberate, strategic decision to create a build, usually for a formal release candidate or a major milestone.
What triggers that kind of high-level decision? It can't just be a developer pushing a button.
No, it's a management decision, and it's driven by data from the requirements management system. That system lists all the features and bugs for a release. When leadership scrum masters, product managers, sees that, say, 7 out of 10 priority features are marked development complete, a report is generated. And that report is the justification.
Yes. The manager looks at it and decides if enough work is done to justify pulling the trigger for a major build. It's content-driven, not time-driven.
So once the trigger's pulled for that big, high-stakes build, how does the system handle it? I imagine a full product build could take hours.
It can, which is why modern systems use parallelism. The build management system pulls all the right files, and a key efficiency is spreading that load across multiple dedicated computers, usually virtual ones, to allow parallel processing, like splitting one big assembly line into 4 smaller, faster ones.
Which cuts down the wait time dramatically. So once that compilation is done, what's the output?
A comprehensive summary report is generated. It lists all the deliverables from the metadata and their current states. Did the mobile app build? Did the API fail? And if it failed, there's a direct link to the error log. The manager reviews this.
And what happens next?
Based on the report, they update the metadata. If it all looks good, they change the state to pass to testing. But here's a really crucial distinction our sources make. Not all successful builds go straight to the testing team.
Why would you run a massive build and then just keep it internal?
Sometimes you do a build just to check the packaging, the installers, the deployment scripts. You want to make sure all that machinery works correctly. Even if the feature set isn't quite ready for a full QA cycle, it's like a dress rehearsal.
That makes a lot of sense. Okay, so that brings us to the second type, continuous integration, or CI, builds. This sounds more tactical.
That's a perfect word for it. The purpose of a CI build is just a simple, tactical sanity check on code that was recently checked in. It's about immediate feedback for developers.
Can you give us a quick example?
Sure. A developer checks in, say, 20 updated Java classes. That action could trigger an automated build of just that one subsystem they were working on. The system runs the build and immediately notifies the developer of the outcome.
If it fails, they know they broke something within minutes, not hours later.
That is the promise of CI. But there are some practical challenges, especially on large teams. If you have 1,000 developers, constant building can just grind the system to a halt.
And you mentioned something about false errors.
Yes. Let's say developer A checks in a database change that needs an application code change from developer B, but B hasn't committed yet. The automated build will fail. And that's not really a code flaw, it's just an incomplete commit chain. If you get a cascade of those all day, the reports become meaningless noise.
So the goal is integration, but doing it immediately causes chaos. What's the common solution?
The common solution is actually scheduling. So CI processes are more likely to run once or twice a day at fixed times like 8 a.m. and 1 p.m. It's a little less continuous, but it's far more practical. It lets developers check in their work, knowing a big sanity check will happen later, and they can review the clean results. It's a balance.
Right. It balances that immediate feedback with just, resource management.
Okay, so whether it's a big planned build or a scheduled CI build, the goal is getting a clean product to the next group. Let's talk about that final step, the clean handoff.
This is the definitive end of the build phase. It's the moment we prepare for the next team, which is usually the quality assurance or testing team.
And that all comes back to updating that metadata we talked about earlier.
Absolutely. Once the decision is made to pass that specific build with its unique build version number to testing, the manager updates the project metadata. The state field gets marked passed to testing. That is the official audible cue for the next team to start their work.
And this is where we really see the payoff. Talk about the modern advantage this gives the whole pipeline.
The advantage is parallel movement. It's velocity. Because we know the specific build is clean and consistent, the testing team can immediately start their work. There's no confusion about which files to use or where to get them from.
And meanwhile, the development team isn't just sitting around waiting for feedback. Exactly. The dev team can efficiently move on to the next set of work, the next time box, the next sprint. They start on new tasks without waiting for feedback on the last build. It means development and testing can operate independently and in parallel, which just drastically increases the throughput of the whole organization.
So this whole detailed process, the metadata, the gatekeepers, the two build paths, it's all about consistency, control, and verifiable quality. It's trading human guesswork for machine reliability.
It is the engine that ensures the integrity of the product. By removing human variability from the compilation step, you maximize reliability and allow your teams to maximize velocity.
And here's where it gets really interesting. And this is the thought we want to leave you with. This whole process has created what the development team thinks is a perfect product. It's tracked with a precise build number, and it's been formally handed off. But what happens when the testing team inevitably finds faults?
That is the crucial pivot point in this whole cycle. Finding a fault isn't a failure of the build system. It is the beginning of the feedback loop that decides if this perfectly built thing ever actually makes it to the customer.
So a question for you to think about. Now that the clean build is in the hands of the quality experts, what does the system do when the feedback comes back? This perfectly built product is imperfect. We'll catch you next time for the next deep dive.
Until next time, keep exploring, keep questioning, and keep diving deep. Thank you for listening to today's podcast. Please feel free to click on the link in the description below to discover more podcasts.